as we have already discussed before, in this type of collision, that is what elastic collision, there is absolutely no loss in kinetic energies between the colliding bodies, right? So we are considering the same situation as we used for deriving the value of coefficient of restitution. That is, we have considered a body of mass m1 initially moving with velocity u1, and in the same direction we have another body of mass m2 moving with velocity u2, right? This is the initial phase where both the bodies are approaching each other, where relative velocity of approach would be u1 minus u2 or u2 minus u1. It would be u1 minus u2 because we have considered that u1 is greater than u2, right? In the second phase, they interact with each other, that is, they just collide, and you can show it by this, that the forces are acting like they interact in terms of their momentum, that is linear momentum and kinetic energies, right? But sometimes you can even skip drawing this part. And in the last stage, after the collision, what happens? This body m1 is now traveling with velocity, final velocity, which is v1, and another body, this m2, is now traveling with final velocity v2. So this time, as per elastic collision theory, the energy of body 1 is going to get transferred into energy of body 2. So we will suppose that v2 is going to be greater than v1 because initially u1 was greater than u2, right? So this gives me v2 is greater than v1, and hence the relative velocity of separation is v2 minus v1, and that is how we derived the value of coefficient of resilience, that is v2 minus v1 over, that is coefficient, that is relative velocity of approach, which is u1 minus u2, right? So we have just revised the concept of coefficient of resilience. Now we'll start with we have to do what? We have to find the value of this v1 and v2 in terms of u1, u2, m1 and m2. So to start this derivation, I'll start it with the linear momentum principle, that is the law of conservation of linear momentum. And to use that, what I'm saying is total momentum of, or total linear momentum of system before collision is, total linear momentum is what? m1 u1 plus m2 u2, right? Mass into velocity, that is mass into initial velocity plus mass into initial velocity. This is total initial momentum. Since this derivation is a bit large, I might have to decrease the font size, but let's do it in normal way. m1 u1 plus m2 u2. After the collision, what is the total final linear momentum of the system? It would be m1 v1 plus m2 v2. I'll write it here only. Total final momentum, which is m1 v1 plus m2 v2. Now, according to law of conservation of momentum, what do we know about it? Total linear momentum of a system remains conserved, that is total linear initial momentum would also be equal to total final momentum. So these two quantities are absolutely equal. From these two terms, if I want to take m1 common out, I am taking this term there, I will be left with m1 u1 minus m1 v1, which is equal to m2 v2 minus m2 u2. This quantity has come here. From this side, m1 u1 minus v1, m1 has been taken common out. Similarly, m2, we are left with v2 minus u2, right? Give this equation some name. Let's say this is equation 1, okay? Same ways, do the same thing in terms of kinetic energy. Total kinetic energy of the system initial would be total kinetic energy for initial phase was half m1 u1 square plus half m2 u2 square, right? And total final kinetic energy would be equal to half m1 v1 square, kinetic energy of this body, plus this, plus half m2 v2 square. Again, I want to take out m1 common from two terms. Also, half is common throughout this equation, so just cancel out half from each term. Now, m1 u1 square minus m1 v1 square, right? Minus m1 v1 square, this gives you m2 v2 square minus m2 u2 square, okay? So, from here, if I am taking m1 common out, I am getting u1 square minus v1 square. This is equal to m2 v2 square minus u2 square, right? This is second important equation. So from these two equations we are going to get the value of v1 and v2, but before that we have to divide equation 2 by equation 1. So since I have less space left, I'll just rub whatever which is not required. So I hope you guys have paused the video right now, I've noted it down, right? We are left with two equations only, and sometimes when you don't remember while deriving the derivation, sometimes you might feel confused that you are going in a wrong direction or the equation is not getting right. Don't think about it and try not to learn the whole formula, rather try to always deduce the whole expression, because that will always give you the right answer. It will save a lot of your time as well as your marks, okay? I want to divide this equation with that equation. So dividing these two equations, I'll be left with this over m1 u1 minus v1. This is equal to this over m2 v2 minus u2, right? From here, these two terms gets cancelled out, these two terms also gets cancelled out, and we will be left with u1 square minus v1 square over u1 minus v1, and here v2 square minus u2 square is equal to v2 minus u2. This term, which is in the format of a square minus b square, can be rewritten in terms of a plus b and a minus b. So here I am rewriting this thing as u1 plus v1 multiplied by u1 minus v1. I have just applied the formula of a square minus b square, right, which is a plus b over a minus b. This was upon u1 minus v1. This is equal to, similarly here, v2 square minus u2 square is v2 plus u2 into v2 minus u2, right? This whole divided by v2 minus u2, alright? This is the final step. From here, okay, I actually needed the equation 1 which was written here, so I'll go back and write it down, but first, from these two equations, what do we get? We can cancel out these two terms and these two terms. So we get u1 plus v1 is equal to v2 plus u2, or if I am taking u2 that side, u1 minus u2 is equal to v2 minus v1. What is this term, u1 minus u2? This is the relative velocity of approach. This term is relative velocity of separation. So if I bring this part down, I'll be left with 1 is equal to v2 minus v1 over u1 minus u2. So this is actually coefficient of restitution. So 1 is equal to E. This is what this equation is giving, right? So in a way we have just proved that the value of coefficient of restitution in elastic collision is 1, okay? Now our basic motive in this whole derivation was to find the value of v1 and v2 in terms of m1, m2, u1 and u2. So to do that, what I am doing is, from this equation, which is the major equation, from this equation I am taking the value of v2. v2 is equal to v1 plus u1 minus u2. I have just taken this v1 on the other side. So I am left with this equation. Now I have to put this equation into what I got after deriving from the conservation of linear momentum, and that equation was, I don't have to go back, I can do it again. How did we do that? m1 u1 plus m2 u2 was equal to m1 v1 plus m2 v2, right? And we brought this term here. So m1 u1 minus m1 v1 is equal to m2 v2 minus m1 or m2 u2. In this equation, I took m1 common out, and then we were left with this equation u1 minus v1, which is equal to m2 v2 minus u2. So putting the value of v2, this from that equation to this equation, you will find the value of v1, but you won't have to do these two steps again. Reason being, I have deduced this equation from the main equation, which is the law of conservation of momentum, right? So rather than doing this whole thing again, just put the value of v2 directly into this equation. m1 what I have is, I'm writing this equation first on the LHS side. So m1 v1 plus m2, instead of v2 I have this whole term, which is v1 plus u1 minus u2. This is equal to this side, m1 u1 plus m2 u2. Alright, so expand this or open the brackets, you will be getting m1 v1 plus m2 v1 plus m2 u1 minus m2 u2 is equal to m1 u1 plus m2 u2. Okay, are there anything common? First of all, I want the value of this v1, okay, which is in these two terms. So I am taking v1 common out from these two terms, and I will be left with v1 m1 plus m2 first of all. Number two, if I take these two terms in that side, what I will be left with is m1 u1 plus m2 u2, m1 u1 plus m2 u2. This term goes here minus m2 what? Minus m2 u1, and this term is here on the with positive sign plus m2 u2. So you can see m2 u2 and m2 u2 are twice. That means this equation becomes twice m2 u2. And what about these two terms, m1 u1 and m2 u1? From these two terms I can definitely take out u1 common. So I will be left with u1 times what? m1 minus m2. And here this is twice of m2 multiplied by u2, right? This is the final values for what? v1 is equal to m1 plus v1 multiplied by m1 plus m2. So from this whole equation I'll get the value of v1 as multiplying or dividing this whole term by m1 plus m2. So instead of dividing this whole, see what I'm doing is I'm taking this whole thing down to or the denominator side of this equation. So I had to write this, right, m1 plus m2. But instead of writing it as whole, I am separating it for both the terms because denominator can be separated. So here I will be left with one this term with this denominator and another this term with this denominator. So I won't disturb this equation here, which was m1 plus m2. I am going to do what I just said, and final value of v1 would be u1 m1 minus m2 upon m1 plus m2 plus twice of m2 u2 over m1 plus m2. So this is the final answer or for the value of final velocity attained by body 1, that is value of v1. If we want the value of v2, what we are going to do, we are going to put this value v1 in any of the equation. Let's say this equation, we'll get directly the value of what? We are putting the value of v1, so we are going to get the value of v2. Let's try it out. So in anywhere throughout the video you want to write anything which you have missed, because I am erasing a lot of stuff, you can just pause the video or go back again to watch it again. Okay. Now what we have to do is we have to find the value of v2 so that we can actually deduce or we can tell about what will happen if two bodies of equal masses are colliding, or if a body of really huge mass is getting collided with a body of comparatively smaller mass. There are a lot of examples like that. If the one body is at rest, another body is moving, or both the bodies are moving. So for all of those things, I want the value of both v1 and v2. We just derived the value of v1. So for v2, what I am doing right now is I am putting the value of v1 in this equation. So our equation was m1 u1 plus m2 u2 is equal to m1. Instead of v1, I have got this, which is u1. This is u1 m1 minus m2 over m1 plus m2 plus twice m2 u2 over m1 plus m2. But I haven't even completed my whole equation, but I can see that this way it is going to get way lengthier. So because this is the method which has been used in your help books, like different or whatever help books you are using, I'll use another method. Instead of going it throughout the long way, I'll rather do it from that shorter way, which was we found out the value of E to be 1, right? What was E? V2 minus V1 over U1, this is V1. V2 minus V1 over U1 minus U2, this was equal to 1. So from here we deduce that V2 minus V1 was equal to U1 minus U2, and the way we started the value of, we put the value of V2 in this equation, I'm going to do the same thing for V1. So here V1 will be equal to, I have brought this V1 here, so I'll be left with V2 minus U1 plus U2, right? And I'm going to put this value of V1 in this equation. Like this was the equation of law of conservation of momentum. And I need this value, the value of V1. So hopefully we'll do it in this much space. M1 U1 plus M2 U2 is equal to, this time I'm putting the value of V1 to find out the value of V2, M1 times that thing, V2 minus U1 plus U2 plus M2 V2. I'll be doing this thing in a bit shortcut, okay? So M1 U1 plus M2 U2 is equal to M1 V2 minus M1 U1 plus M1 U2 plus M2 V2. How many terms of V2? This and this. That means here I have a term where V2 is common taken out, and you will be left with M1 plus M2 multiplied by V2. And that means M1 plus M2 is going to get into the denominator of other side. Then the second thing is, this M1 U1 and this M1 U1 are going to get added up because this negative sign goes here and becomes positive. So M1 U1 plus M1 U1 becomes twice of M1 U1. And lastly, M2 U2 minus M2 what? This thing and this thing. M2 U2 minus M1 U2. So if I am taking U2 common out, I will be left with M2 minus M1 multiplied by U2. So to find the value of V2, taking this on the denominator side, this term upon M1 plus M2 and this term with M1 plus M2. So this is the value, these are the values of V1 and V2. These are the final values which we wanted to derive at the starting of this derivation. So why do we deduce this? Why did we do this? Okay, consider this simple example. I'm not going to erase these two major formulas. I'm just going to take few examples. Okay, consider it this way. First case, I have two bodies of equal mass where one body is moving with some velocity u, another body is at rest. So u1 is equal to u and u2 is at rest. Second case, this body is moving with this m, and also I have also taken the case that both these bodies are of equal mass, right? That's why I did not write m1 and m2, rather I used both m's. This m is moving with velocity, initial velocity is u, and this body of the same mass is also coming towards that body with initial velocity u2 is equal to what? Should I take it u only? No, I will be taking it minus u. Reason being, the velocity is in opposite direction to that of initial velocity of the other body. Third case, these are the two cases with equal masses. Okay, what could be the third case? Let's say there is a very huge mass where this m is greater than smaller m, like huge mass, and this body is moving with a velocity u towards this smaller body of mass small m. This body is initially at this initial velocity u1 was equal to u, and u2 is, this is u2, this is at rest. This is the third case I could think of. Lastly, I can think of another case where I have this smaller body that is mass m. This time again mass is, the capital mass is greater than smaller mass. This body mass m is moving with velocity u, that is initial velocity is u, and it is going towards a bigger mass which is initially at 0. Now in all the cases, what I want the final velocities of each body. So let's do it. First of all, for equation 1, v1 equal to u1, which is equal to u, right? We have a u here, then multiplied by m1 minus m2, both are of equal mass, this term becomes 0. So this whole term becomes 0. Then you are left with 2m2, which is 2m upon 2m, cancels out, you are left with only u2. So v1 becomes equal to u2. What is v1? So its final velocity will be u2. What was u2? 0. And if I put the value of if I try to get the value of V2, what I'll get start with the same thing, 2m upon 2m cancels out, you are left with U1. So V2 is equal to U1. What was U1? U, and this term becomes 0 because these two are equal. So what actually happened, in case of two bodies of equal mass, when one body is traveling towards another body, which we usually see in the game of snooker or billiards, this body will come to rest and that body will move forward with the same velocity, unless and until there is some loss of kinetic energy, and that is always there because we have already described this thing that there are no two real bodies in this world which can perform perfectly elastic collision, because energy definitely gets lost in terms of sound energy or some other energy, right? Also due to friction, that is the major component. What will happen in this case, if you follow the same method, you will see that this body V1 will be minus u and V2 will be plus u. That means when two bodies of equal masses are coming towards each other, they will reflect back or they'll bounce back with the same velocities but in opposite direction. In this case, if a very huge mass is coming towards a very lesser mass, this will keep on moving with the same velocity, whereas this mass will move with twice the velocity of this body. So V1 will remain like u, but V2 will be twice of u. So this body is going to go with twice the mass. And lastly, in this case, this body is quite lighter in size or mass as compared to this body. So this body is going to get bounced back from the same body. So final velocity is going to be minus of u, whereas there will be no change in velocity of this body. So V2 will remain equal to 0. So these are all the possible conditions and the values of final velocities in case of elastic collision in one dimension.